proving similarity and then using that to find an unknown length. We have two triangles here. It says, look at the cool diagram on the left. Isn't it cute? Prove that similar triangles exist, then find x. Question: can we assume that similar triangles exist yet, or do we have to prove it? Well, we have to prove it. They haven't told us that they're similar. They've said that we have to prove that they are similar first. So let's prove that these two triangles are similar. We would need two pairs of matching angles. One of them is, I can tell that this angle right here, this right angle, is obviously the same as this one. Look, they told us they're both 90 degrees. So the angle A to B to C is the same as angle DEC. The reason? Given. Or you can say both 90 degrees. We need another pair of angles that are equal. It might be nice to say that this angle is the same as that one. You can see that they look very similar. But we're not trying to guess here. We're trying to prove it without a doubt. So we can't actually prove that these two are the same. Maybe you might think, oh, I know, they're alternate angles. But no, alternate angles only work if we know that they're parallel lines. So that's sad. What about these two? These ones look the same. And these ones, we can prove that these two angles are identical. Why? Because they're vertically opposite. So the angle from A to C to B, this pointy angle here, is the same as the angle in this big triangle from D to C to E. Cool. Why? Well, it's not given to us, I'll tell you that, because it doesn't tell us that these are the same, but we know because they are vertically opposite. I'm a little bit lazy, so I just write vert.op. Now we've got our two pairs of equal angles. Now, a proof normally finishes with the statement you're trying to prove. Therefore, triangle, well, I've given away the answer here, triangle A to B to C, so that triangle there, that small triangle, is similar to get the order right, A was my first angle here. So the second one, notice that this was the really sharp pointy angle, which in this triangle is D. So that's why I wrote D first. The next angle, we went across to the 90 degree angle. So I suppose I'd better go across to the 90 degree angle, which is at E. And there's only one left. We end up at the last letter, which is C. So notice that I've tried to get the order consistent in the first triangle and the second triangle. Now that we've proven similarity, well, now we can start to find x. One strategy that is useful to help get the matching sides right is to put symbols in these angles. You can see that this sharp point here, this sharp angle, is the same as this sharp angle. Maybe they look the same, but we've proven it. The angle at A in the small triangle is the same as the angle as D in the big triangle. That's what we've proven here. A matches D. So we can say that they're the same and put a little symbol there. I like to use Greek letters. Alpha matches with alpha. These are the same number. But you can use a dot or an X or a black circle, whatever you like. Another two that are the same are beta here and beta here. Again, I've picked the Greek letter beta. You can use a different symbol if you like. Use a smiley face. So now we've named the angles, we've given them each a symbol. Now we can write what the lengths are. This table strategy I quite like, which is where we write the lengths that are opposite each angle. For example, in the small triangle over here, I have the angle alpha and the length that is on the other side, opposite to angle alpha. You can see that it's very far away from angle alpha and doesn't touch angle alpha. The length that is opposite is 3. So we can start filling in this table. In the small triangle, the length opposite alpha is 3. The length opposite beta is... Oh, it doesn't say. Oh well, that's okay. I don't really care. The length that is opposite the right angle is here, so the length that is opposite is 8. In the big triangle, the length that is opposite alpha on the complete other side is 6. The length that is opposite beta is, something. I don't really know. I don't really care. And finally, the length that is opposite the right angle, that is on the complete other side of this right angle, is x. So in that way, I now have that 3 in the small triangle matches 6 in the big triangle, and 8 in the small triangle matches x in the big triangle. You might remember that the ratios have to be the same because they're similar. So you can very easily turn these matching sides into a ratio by just writing it as divide. And this one as well, just write it as a fraction, divide. Now it's a ratio. These two ratios have to be the same. So we can say 3 divided by 6 equals 8 divided by x. What a beautiful way to make the equation. You just read it off the table. And now that you've got the equation with a fraction on either side, you can cross multiply. The x moves from the bottom of this side to the top of this side, so it's 3 times x, equals divide by 6, moves from the bottom of this side, turns into a times by 6 on the top of that side. We've cross multiplied. Now we can write this equation again, but instead of 8 times 6, we can replace that with the answer, which is 48. Now I can go again, but instead of, I've got to multiply by 3 here, so that would turn into a divide by 3 on the other side. So x is 48 divided by 3, which happens to be 16. This is a length, so do I write centimeters here? No. Sadly I can't, because there are no units in the question. I mean, we try to put units, but if there are no units in the question, then our answer won't have units either. Anyway, this is the really comprehensive way to find an unknown length by proving similarity first and then finding the length. Once you get the hang of proofs, they're actually pretty satisfying to be able to prove something. Anyway, it's a tricky concept, but let me know if you have any questions. And good luck. Bye.